You're one that okay. So last Thursday of class, I guess kind of theoretically, certainly next Thursday we will restrict the class unless there's something that I just absolutely need to finish. We'll restrict the class to just review material. So that means that we only have 4 days left of real class, which means the summer is almost over, which is just wrong. It's gone way too fast, way too quickly. You can have 2 weeks of freedom. I have 2 weeks of scrambling to be ready for next academic year. So, because I think instructors always think, I'm going to get so much done over the summer. I'm going to have all of my lectures prepared for next summer, and especially in 3173, there's going to be I'm going to be doing a big changeover in terms of kind of structuring the class for making it look more like it used to. It drifted, and we want it to look a little bit, especially one of the most confusing things is there's all these lab assignments, and it's like they're good labs and they're hard labs, and you will hear people complain about them, but they're good labs, but they don't seem to have anything to do with the coursework anymore, because the coursework drifted over several instructors. And so I'm trying to take it back so that it actually has some relevance to the lab and whatnot. And so I got all these books, and I laid out and said, all right, here are all the things that I'm going to teach, and here are all the new lectures that I'm going to have to put together. And then I didn't have any more time. So I have 2 weeks to try to scramble together, put together a bunch of lectures. And fortunately, at least the first couple of weeks are just the same old. So I'll have a couple of weeks to get caught up. So you guys can go have your 2 weeks of freedom, and I'm going to kill myself for the next couple of weeks getting things pulled together, especially since I also have a PhD qualifying exam on the 25th. So that's just one more thing for me to study for and take up all of my time. But fun stuff. The working world is awesome. So I guess what the plan is going to be for today, as much as anything, is I want to finish up the last bit on power factor correction. It's pretty straightforward. And then we kind of have two-ish options. The first option is we can just cruise into variable frequency circuits and resonant response and all that kind of stuff. If you look at what the class is supposed to cover, it's supposed to be all the DC analysis stuff that we've covered. It's supposed to be the AC analysis stuff that we've covered. And then to some extent this AC power stuff. Those are kind of the key things. Everything else is kind of gravy or icing on the cake. So we can cover this frequency response stuff. We can cover Laplace transforms. But all of that stuff is kind of, some of the introductory material will show up on like prereq exams for the lab and stuff. But you will get a much deeper introduction to things like Laplace transforms in I think Dr. Burrell usually teaches the linear systems class. I think it's 3160. And so you will spend lots and lots of time doing Laplace transforms. And so I can introduce you to the concept of Laplace transforms, and that's fine and good. But you will learn it again, I guess. And so one of the things that I want to give you guys an option, so that's the first option is just jump into this variable frequency stuff and see how far we can get. The other option is kind of to make sure that at least today, that if there's any topic from all of the stuff that we've covered that you're not feeling comfortable with, whether it's Thevenin equivalence or voltage division or whatever, that something is just not feeling comfortable, it still doesn't feel comfortable, that you feel comfortable on that before we jump into this material that frankly, I don't always cover. I don't always get this far in the semester. So, but let's finish up the power factor correction stuff first. I'll give you a chance to ask some questions on the homework as well. But let's do the power factor correction stuff, and then I'll open it up a little bit, okay? So, and I think the homework assignment will, right now I think Monday is a good day. So I'll even say, end of the day on Monday, so like 3:30 or so on Monday if you want a little bit of extra time. But I'll certainly take it if you have it in class. So quizzes I haven't looked at. Again, my excuse is that the online students just got done with the quizzes. Plus I was moving firewood all day yesterday, so I didn't look at them at all. All right, so power factor correction. I've kind of alluded at this, or perhaps even to some extent explicitly noted this, is that industrial loads tend to have a very heavy lagging power factor. And that has a lot to do with the fact that most electrical machinery is inductive in nature. A lot of AC motors, some DC motors kind of things. And in general, those kinds of loads, when viewed from the point of view of the power system, are heavily inductive. They're electric motors. And this becomes bad news for their electric bills. We saw when we looked at those original power factor topics that just by adjusting a power factor from, say, 0.84 up to 0.9 or from 0.707 up to 0.9 can have a significant impact in the neighborhood of multiple thousands of kilowatts. And you start multiplying that by what is the rate for the power that you're paying for, and as the power rates continue to go up, how much is that going to cost your company, especially if you're running that equipment quite frequently. So we want to correct that bad power factor somehow. And that somehow is kind of, we got at that yesterday, which is this concept that inductors or inductive loads consume reactive power, but capacitive loads generate or supply reactive power to the circuit. And if we can use capacitors to supply the needs, or at least some of the needs, of the inductive load, then we can reduce the Q. That reduces the S, the hypotenuse on our Pyre triangle, to a smaller magnitude, and that means that we're going to be paying a little less for our power, and that's a good thing. And so we're going to do that by figuring out what is the appropriate capacitive load to place in parallel with the rest of our load in order to fix that power factor. And that's going to be the overall goal here. So again, the idea here is that we want to reduce Q. Just as a reminder of our power triangle kind of dealy-bop here, we've got S along the hypotenuse, we've got Q on the vertical arm of the triangle, and we've got P over here. And the is that we want to reduce reduce Q so that we have a slightly flatter triangle. And so Q new is somehow less than Q old. That's kind of the goal. In this, P is going to remain the same. P old and P new are going to be exactly the same quantities. And the part of the goal here is to make S new, we want S new to be somewhat less than S old, but P old and P new are going to be the same values. We're not going to change, the machinery itself is still going to operate at 88 kilowatts or whatever else the load might be, and we're not going to change the voltage. We're still going to be taking in 480 volts or 220 volts or whatever it happens to be. But we want to change, what we want to do is we want to change the amount of reactive power we're kind of requesting from the power system. So we can quantify this a little bit mathematically and say, well, that old capacitive power, or that old complex power, is equal to the old real power minus the old complex power, or reactive power. And we can express that as a phasor as some magnitude s at an angle of theta old. And that's the power factor angle for the load as it exists now. And so then let's quantify what our goal is at the same time. So our new complex power is going to be some p nu minus jq nu. And that's going to be s nu at some angle theta nu. So if we start if we look at what is the difference between what we have and what we're aiming for, and we take the difference of those two, that'll tell us what is the complex, or what is the reactive power, because it's all going to be reactive power, that we want to generate from our capacitors in order to fix this power factor. So that just means that whatever the difference is between the new and the old complex power is going to give us what we need to generate from our capacitors. Well, let's plug in our formulas here. That's P old minus JQ old minus P new minus JQ new. So what that's going to give us, at least, where'd the pluses come from? My slide is very strange. Up on the top it's got minus JQ old, and at the top, on the top and down in the bottom, all of a sudden it magically changes to a plus. Oh, are we just... No. I think that there must be a typo in the top part. I don't think it's supposed to be minus JQ old. I think it's supposed to be plus JQ old. Either way, the old and the new real power cancel out. They don't exist anymore because they're the same value. That's not going to change. And the power that needs to be generated by the capacitor is going to be, let's see if I can make sure this is right. Yeah. It's going to end up being Q new minus Q old is what needs to be generated by the, so that's okay. Is what needs to be generated by the capacitors. And realistically, that's just the subscript. That's just going to be reactive power. There'll be no real power that's generated by the capacitors. So that's the goal. That's the idea that we're working with here. We have some old complex power, we have some new complex power, and the difference between those two is going to tell us what is the amount of capacitive power that needs to be generated, and then knowing what we know about how much power is created by a capacitor, we can figure out what the value of the capacitance needs to be. So that's what's on the next slide, is a comprehensive power factor correction strategy. And so what we need to do is, based on the current situation and the same kinds of analysis techniques that we were working with complex power the last couple of days, we want to find what is the current reactive power needs that we have. And we're going to use that, we're going to find that based on the current real power needs of our load, as well as the current power factor, or at least the current power factor angle. So either one of those two works. It doesn't matter. As long as you have two of those things, at least the real power and either the power factor or the power factor angle, because if you have the power factor, all you have to do is take that inverse cosine and you have the power factor angle, right? So we find what the old situation is and quantify that. At some point you have to decide, what is my goal? What is the power factor that I want to have when all of this is said and done? One question that I don't know that I have a good answer for is, why not shoot for 1 all the time? If we want a unity power factor, why kind of stick with a 0.9 or lagging power factor? Why not push it up to 0.95, 0.99, something like that? And I don't know what the answer is to that question. But we will have a target power factor, and we will run with that, and we'll find what our theta nu is supposed to be based on that new power factor. And then our new capacitive power will be, we'll just plug it into this formula. The new new reactive power will equal the old power, real power, times the tangent of the new power factor angle. So that's an important formula to remember. Definitely write that one down, highlight it, whatever, because that's going to be kind of the key thing for figuring out what's going on with power factor correction. Then once you have your Q new, you already have your Q old from up here, so plug it in. That will tell you what the capacitive power need is supposed to be. How much reactive power do I need to generate to get to where I want to be? And then you can figure out what C is. What is the value of the capacitor that I need to go buy, or bank of capacitors or whatever, using negative omega times CV squared. And that will give us the value of the capacitor to go buy. Perhaps the only reason to not try to go really far is it may be tremendously expensive to buy a bank of capacitors that can handle a 220 volt inputs and not melt, I suppose. So here are a couple of quick examples of doing this kind of power factor correction. We have an inductive load. It's an induction motor. It's consuming 50 kilowatts of real power, and the power factor is 0.8 lagging. So that's pretty straightforward. 220 volts across the source. It's at 60 hertz. Here's a time when we do need, in all of the other complex power questions, the problem was frequently stating, yes, it's operating at 60 hertz, but we didn't need to know that particularly. Here we do need to know that because we can't figure out what the capacitive power is without knowing what omega is, what our radiant frequency is. So we need to know that. And so the question is, if we want the power factor to get up to 0.95 lagging, what is the value of the capacitance that we need to add? So let's put all of these things down so we kind of get it all together. The real power, so P old, in terms of our old equations, is 50 kilowatts. Our old power factor is 0.8 lagging. Our old voltage and our new voltage is going to be 220 at an angle of 0 degrees volts. And that is an RMS value. The frequency is 60 hertz, which means the radiant frequency is 377 radians per second. And our new power factor that we're shooting for is 0.95 lagging. So that's just, again, taking everything from the problem statement and just kind of condensing it down here. So some of the stuff that we're going to start with is going to be exactly the same as our solution strategy for solving for complex power that we did the last couple of times. And that first step was, well, what is the old complex power? And so what we can do is we can divide our real power, the 50 kilowatts, divide that by the power factor itself. So, and that's just P divided by the power factor. And that gives us the magnitude of the phasor value of the complex power. Divide 50,000 by 0.8. And that tells us that the magnitude of S old is 62,500 volt amps. So that's the first step. The second step is, what is the angle of that phasor? And that's just taking the inverse cosine of theta, which is 0.8. Well, I guess it's the inverse cosine of the power factor, which will give us theta. So inverse cosine of 0.8 gives us 36.87-ish. And that is theta old. So that means that our old complex power in general, totally was 62,500 at an angle of 36.87 degrees volt amps. But the whole point of doing this and taking what we have is we want to find out what the heck is the complex power, the reactive power. That's what we're looking for here. So let's take and get that into a rectangular form, which is somewhat more useful to us at the moment, or whatnot. So we get 50,000 plus J 37,500 volt amps. So this is what we were solving for in the first place. That's the whole reason we were doing this. We wanted to find out what the complex load is, and so this is the exact same step there. But the reason that we went through all that we went through was to find out what that was. I suppose see what it was. It was the tangent of the power factor angle should give us, it was Q over P, right? Opposite over adjacent. Yeah. So that should give us the same value. So if we multiply, so that means that Q equals P times the tangent of theta old. This should give us the same answer. So we have 50,000 times the tangent of 36.87 is 0.75. Yeah, that gives you the same answer. So here's the long way. This is the short way. They'll give you the same answer. So use whichever one kind of feels good. This one is using what we know about the power triangle on the top. The one on the bottom is getting more directly at the power triangle stuff and saying, look, if we multiply, the tangent is the opposite over the adjacent, so that's Q over P, and then we can figure out directly and solve more directly for Q instead of going through all of this stuff. You still need to know what this is. So you have to perform that inverse cosine of the current power factor to figure out where you're going. So the point was we wanted to find out what the current reactive power need is, and it happens to be 37,500 volt amps reactive. So that's our old desire. Kind of where do we go from here? Well, we need to figure out what is our new power factor angle. Our theta new will equal the cosine, or the inverse cosine of our desired power factor, and our desired power factor was 0.95 lagging. So from that inverse cosine, 0.95, which gives us a new power factor angle of about 18.19 degrees. That's what we're shooting for. And so now we can use that same basic formula that we had before, that the new reactive power will equal 50,000, which is P, times the tangent of theta nu. So that would be the tangent of 18.19 degrees. 50,000 times the tangent of 18.19 is 16,429. Perhaps for the sake of easy math, we'll just call it 16,430. I guess, strictly speaking, it's 16,429.549, something like that. So so now we subtract Q new minus Q old will give us Q capacitive. So that is Q new was 16,430 minus 37,500, which is what we calculated before. This was our old capacitive power. 16,430 minus 37,500 is negative 21,070. And so then we plug that into our good old equation that, let's write the general form of the equation. So that equals negative omega CV squared equals negative 21,070. So we can divide by the negative omega v squared, and that will leave us with just C on that side. The negative signs cancel out. So you've got 21,070 divided by 377 times the square of the voltage, which was 220, and an angle of 0. 21,070 divided by 377 times 220 squared gives us a fairly small value of 1.15 millifarads. So that's the value of the capacitor that we'll place in parallel with the rest of our load to figure out, to fix our power factor and bring it up to something somewhat more respectable. Now, to me, not spending an awful lot of time with real circuits and real circuit components like this, it doesn't seem like 1.15 millifarads is a particularly big capacitor, but it does need to be able to handle a 220 volt source. So that may require a fairly large capacitor to make that happen. So let's see. Why don't you guys try this one? You've got all the notes in front of you on how to do this. So you guys try this one. This is all of the information you'll need, and it'll give you the whole strategy to do the solutions in the homework. So our old power, and our new power for that matter, is 100 kilowatts. The old power factor is a pretty horrible 0.707 lagging. And that's pretty bad. We need to fix that one. The 60 hertz line that is supplying this load is at 480 volts at an angle of 0 degrees. For what it's worth, the impedance in the line is 0.1 ohms. And our goal, our new power factor goal, is going to be 0.95 lagging. So, what is the value of the capacitor or bank of capacitors that we need to raise that power factor up? So give it a couple of minutes, try to work that one out. There may be more information here than you need. Okay, so this work takes us. I've done a lot of the work that takes you most of the way through it. So if we have a power factor that's lagging at 0.707, the inverse cosine of that tells us that our old power factor angle was 45 degrees. 45, 45, 90 triangle means that it's essentially the opposite and the adjacent. It's going to be they're going to be the same, but you can find that out mathematically as well. If you multiply the old power, real power requirements by the tangent of 45, tangent of 45 is 1, and so the old capacitive, or the old reactive power was 100,000 bar. So that was the old situation. What's the new situation? Well, we take the inverse cosine of our desired power factor of 0.95, which is 18.19 degrees. We're going to run through the Q new equals P times the tangent of 18.19. And it gives you around 32,859, depending on exactly where you do your rounding. That number is actually a little different than my notes, but so then we plug those numbers into here. The new reactive power component minus the old one gives us a difference of negative 67,141 bar. And so that's what we need to generate with our capacitors. So what we can plug that last bit in. We say that negative omega, omega c v squared equals negative 67,141. The negatives essentially go away, so C equals 67,141 divided by omega v squared, which was 377, divided by 377 times 480, 480 squared. And so 67,141 divided by 377 times 480 squared. It's a very small number. It happens, if you put it into something reasonable, it's either 773 microfarads or I guess that would be 0.773 millifarads, if you want to put it that way. So again, that seems to me to be a fairly small capacitance value, but finding a capacitor that can deal with a 480 volt source is probably going to be somewhat tricky, even if it is a fairly small capacitance value. So that's power factor correction. It's more or less. You have a question? Or?
Oh yeah. So assuming that you have leading load in your facility, could you do a power factor correction with using a inductor as your solution? I guess that would probably be very unlikely to happen, but
Yeah, I suppose I would guess that the same kind of situation could occur, that you are generating too much reactive power, and so you put something in that consumes that reactive power for you, but it seems like it would be fairly hard to get that situation to occur. But it would be interesting to hear from someone out there in internet land that has actually seen such a situation occur. But it seems like you could, and I think that the same basic problem-solving scenario could be applied to figure out what's going on. So that's power factor correction. That's the end of the power stuff. So let me wrap up the chapter, sum it up in a couple of slides real quick. That will kind of bring us to the end of this one. So instantaneous power was the first one we talked about. It is a function. It gives you, there's an average DC component, and there is a sinusoidal term with a frequency that's twice the voltage or current. So the formula would be given to you on a final exam. It's something like Vm Im over 2 times the cosine of theta v minus theta I plus cosine of 2 omega t plus theta v minus theta I. No, plus theta v plus theta I. That's your instantaneous power formula. And so it's, again, it's exact, but it's not handy to carry that kind of formula around. We would like a number. So we can use average power to get us that. So we multiply the voltage times the current, the magnitudes of those two, times 1/2, and then times what we know is the power factor, or just cosine of theta v minus theta I. And that will give us the average power. Average power of resistive loads. You can either do the V times I bit, or you can also do an I squared R times 1/2, and that will get you the average power. Because the voltage and current are in phase, the cosine term goes away. For reactive loads, their average power is going to be 0 because the cosine term goes to 0, and that will overwhelm anything else that's going on. Then we talked about RMS values. You can replace the Vm Im over 2 in your average power formula if you want to by using RMS values, and then just use VRMS times IRMS times the cosine of theta v minus theta I, and that's going to give you your average power as well. Basically what it boils down to, and your rule of thumb that you need to take forward going into power class and whatever, is that if you have an RMS value and you multiply it by the square root of 2, that's going to give you your peak value. If you have your peak value, you divide it by the square root of 2, and that will get you your RMS value. RMS value is the most common way that I'm aware of that people deal with power situations when we're looking at it. So if you dig out an incandescent bulb, or you start thinking about what's going on in a wall socket, and you're hearing about RMS values. Then we started looking at power factor stuff, and there's a lot of stuff going on there. Your apparent power is measured in voltamps, and it's just the RMS current times the RMS voltage. The power factor is the ratio of the average power to the apparent power. I guess that's a fancy way of putting it, but it just kind of relates what's going on. If the power factor is leading, that means the current is leading the voltage. That is indicative of a capacitive load. If the power factor is lagging, the voltage is leading the current, and which is it's an inductive load. You can correct lagging power factors by putting capacitive loads in parallel. And you can also use all that stuff about the power triangle to figure out what is the overall complex power in terms of S equals P plus JQ, where P is the real power, Q is the reactive power, the quadrature power. That's measured in voltamps as well. The last thing, if you are trying to calculate the complex power, S equals V times VRMS, the phasor version of that, times IRMS conjugate. Conjugate. Don't forget the conjugate. So that when you're doing that calculation, regardless of which direction you're going, don't forget the little star. Don't forget to flip the sign of the angle, or change the sign of the rectangular representation of the number. So, and that in some respects is kind of the end of the circuit stuff. I mean, we can make applications of these other things to circuits, especially the next chapter is going to look at resonant circuits, and so I know enterprise students have already looked at this stuff to a large extent of how do you build a filter out of a resistor, a capacitor, or whatever, that kind of stuff. But before I go on, are there any questions about any of the material that we've covered this far? Any of the homework questions? I wanted you guys, I remember talking to Dr. Mbardar, not this past spring, but the spring before, and he asked me how circuits was going, and I said, well, it's going good. I don't know that if we're going to get much of the resonant circuits or the Laplace transforms covered, but we've gotten most of the rest of the stuff pretty good, I think. And he said, yeah, that's really the important part. So if he says it's the important part, that's good enough for me. So is there anything from the previous chapters that you guys are not feeling comfortable with? Anything? Okay, let me just tee this up. I'm going to shoot to get you out of here at 10:30 because it's been a long week, and I think for everybody. So let's get this flipped over to the right. So we've kind of perhaps even hinted at this a little bit before, and it's the concept that circuits behave differently at different frequencies. And you know, we looked at what is the value of the impedance for an inductor? Well, it's j omega times L. So if you start playing around with the value of omega, that's going to start changing the value of that impedance. And that's kind of the key for all of this stuff. And you know, we don't, it's very common for things that are plugged into the wall, they're only ever going to operate at 60 hertz, no big deal. But any kind of radio transmitter hardware or a lot of different other pieces of circuitry will operate at lots of different frequencies, and it's helpful to be able to use that to do interesting things, to filter out signals that you don't want or to reinforce signals that you do have. And that's what we can look at with all of this stuff. So we're not going to look at all of the material from this chapter. This is chapter 12 in the textbook. We're going to kind of pick and choose some of the early topics, and then we're going to jump into Laplace transforms, assuming we have time. So essentially what we're going to look at is variable frequency response analysis. So to start off with, just kind of what happens when you start messing around with omega, when you start messing around with the frequency that the circuit is operating at. What does that do to the circuit? We'll look at a couple of easy transfer functions, nothing particularly hard or special, but just to show you that you were introduced to transfer functions in DSP, right? Yeah. So this is where transfer functions come from in the first place. I mean, I think that for the most part in DSP they kind of said, here's a transfer function, right? And well, where do those transfer functions come from? Well, they come from the underlying circuits, and so we can look at that a little bit. We will look at something called a Bode plot. A Bode plot is a kind of a back of the envelope kind of calculation that allows us to visualize how a circuit will behave over the frequency spectrum. We'll use it. It's one of those things that you can almost look at and say, why do we need to learn this? When we have things like MATLAB and PSpice and these computer programs, where all I have to do is say, here is my circuit, tell me what my transfer function is, tell me what my frequency response looks like. Why do we need Bode plots? And that's because as much as, I'm a computer engineer by trade, I do lots of programming, and I know that the software is not always right. We try, but it doesn't always work out that way. And as a brief story, my wife is a mechanical engineer. She was working with, and her senior design project was working on a wing design for an airplane. And after they had put it into this program called Fluent, which is a fluid dynamics simulator, and for the most part, you can fairly safely work with air as a fluid, actually, and It's complex, but to a large extent, Bernoulli's equations of pressure are kind of what allow us to understand how planes and birds and stuff can fly. So they put this model of their wing into the software, and they hit the go button, and it came back and said that the wing actually had negative drag. And essentially what that means is that if you were to set the wing on the ground, it would just kind of take off all by itself. And obviously that's the kind of thing where you go, maybe the software is not right, but without some sort of intuition about what negative drag is or what you kind of think your circuit is supposed to do, how do you know that what you're getting out of the software is meaningful? And so that's why the Bode plot still has some amount of relevance. And then we'll look at some specifics of resonant circuits. Some of the concepts almost seem kind of random. We'll define something called the quality of the circuit, or just the Q of the circuit. We'll look at how to calculate what the actual resonant radiant frequency of the circuit actually is, and all that kind of good stuff. And that will, after that, it gets into filter networks, and we're not going to talk about that so much for two reasons. The biggest one being it relies a lot on op amps, which we did not cover and gets covered in electronics class. And the second thing is it would take a lot longer, and we wouldn't ever get anywhere close to Laplace transforms. So a couple of quick drawings, really quick. When we start looking at frequency response of the impedance of some of our normal circuit elements, we will see not entirely unexpected behavior. For a resistor, the impedance equals, well, it equals R. So what happens if you start messing around with omega? Well, how does the impedance change? So let's put Z, the impedance on this axis, put omega on this axis. Yeah, that's not real interesting, but that's the behavior. What about the phase? Well, let's make this the phase angle theta. Let's make this omega. How does the phase angle change as you go over frequency? It doesn't. It stays fixed at 0. In the the voltage and current always stay in phase. So there's not really anything interesting there. But what it does tell you is that regardless of the frequency, the impedance of a resistor is going to stay fixed. Okay. Well, let's look at something that's not quite so boring. What if we look at an inductor? That value in the impedance of an inductor is J times omega times L. So in terms of the magnitude of the impedance, regardless of this J term, if we start looking at what is the value of the impedance with frequency, it starts out at 0 and goes up with a slope of omega L, I guess. So it's just it's a nice straight line. So it linearly increases with frequency. The phase, on the other hand, isn't particularly interesting. It just hangs out at plus 90 degrees. And that's because of the positive J up here. Two more pictures. Capacitors. The impedance of a capacitor is negative J upon omega C. So if we start playing around with omega there, well, as omega approaches 0, that's going to be a really big number. As omega goes out towards infinity, that's going to drive this to a really, really small number. And so your impedance with respect to frequency of an inductor is going to start up here somewhere and then come down like this. A pretty traditional 1 over a times x, kind of function. Basic idea there. And the frequency of and the phase response with respect to frequency is just going to hang out at negative 90 degrees. And that's the negative j bit. So again, nothing surprising, nothing weird. Where it does get more interesting is what if we designed a series RLC circuit? How does that one react with respect to time? So we just have a circuit, it's got some sort of input voltage, and there's an inductor, there's a capacitor, and there's a resistor. The resistor has a value of R, this has a value of C, this has a value of L. Some voltage, doesn't matter. The overall impedance seen in that network is just the impedance of the inductor plus the impedance of the capacitor plus the impedance of the resistor. And we've done a couple of homework problems and quiz problems, test problems, where we calculated what that impedance actually was. So what is it? Well, let's make that somewhat more interesting. That's R plus j omega L plus 1 over j omega C. Well, let's kind of clean that up a little bit. Multiply through with some terms and whatnot. And we can transform that into j omega squared times LC plus j omega RC plus 1 over j omega C is what you get if you if you rearrange the terms. And we'll see as we go forward that there's some good reasons for arranging the terms in this specific way. But essentially you're multiplying through by j omega C in some various places. So this one has the j omega squared LC comes from here, the j omega RC is here, and then that one's up there. So if we look at what is the frequency response of this one, this is where it gets somewhat more interesting. Impedance on that axis, omega on that axis. It starts out looking very much like the capacitor, but then once it gets to a certain frequency, it's going to start acting like an inductor. So at low frequencies, the capacitor dominates, and it's that thing in the denominator that makes that happen. At higher frequencies, it's this LC component, especially the j omega squared part, that drives this one. And the interesting kind of break frequency here is 1 over the square root of LC, which should look familiar. That was omega naught in our second order transient analysis. The same essential thing occurs with the phase if we start looking at that. If we put 0 here as the midpoint, positive 90 up here, negative 90 down here, it's going to start out close to or at negative 90, and at that same break frequency of omega, it's going to come up near 90 degrees. So, in other words, the capacitor dominates at low frequencies, the inductor dominates at high frequencies, and there's some transition period around that same frequency, omega naught. There's some more interesting ways to kind of quantify all of that stuff, and we will take a look at that going forward. There's some relatively interesting stuff in this chapter, which we'll look at next week. Homework should be due at the end of the day on Monday if you'd like the extra time. Otherwise, you can turn it in class on Monday. Have a good weekend. I'll be in my office definitely today and most of tomorrow if you have any questions. Have a good weekend, guys.